Friends, our subject is manufacturing processes 2 and we are continuing module 1, classification of metal removal processes and machine tools, and this is the second lecture under the module 1, and the content or instructional objectives of this lecture 2 are: state the working principles of machine tools, the basic principles. Under that, illustrate the concept of generatrix and directrix, demonstrate tool work motions, give idea about machine tool drives. B, show configurations of machine tools and state their uses. C, state how machine tools are specified, the conventional machine tools, central lathe, drilling machines, milling machines, shaping machine and planing machines. And last, D, classify machine tools with examples. Now, say A, the working principles of machine tools. I remind you, machine tools, they produce geometrical surfaces. This was mentioned in the previous class also. Now, when we say geometrical surfaces, we mean flat surfaces, cylindrical surfaces and contour surfaces which can be mathematically expressed and redrawn according to program. Only those will be called geometrical surfaces. Now, major functional components of machine tools. A machine tool is comprised, all machine tools will be comprised of some common features, which are devices for holding the job and the tool. For example, in lathe, the jobs are held in chuck or the driving plate. Tool is a tool holder or tool post. Next, drives. All machine tools require power drive for moving the tool and the job. Now, the kinematic systems mean a chain of mechanisms to transmit motion and power from the source, that is motor, to the tool and job. And these mechanisms comprising the kinetic motion system can be belt pulley system, can be chain and sprocket, can be gears, worm and worm wheel, ratchet, pawl and rack pinion and so on. Next is automation and control system. Some machine tools are semi-automatic or automatic, so some automatic features are there, and control system to control the process parameters, speed, feed, depth of cut, etc. Now, last, the structure or body of the machine tool, that is a big housing, it remains stationary and that should be strong and rigid. Now, machine tools produce geometrical surfaces on the job with the help of the tool. To accomplish that, some motions, tool work motions are necessary, and there are generatrix and directrix. These are two vectors and we have to just understand conceptually, and with the help of generatrix and directrix we can explain a lot of activities of the machine tools. For example, so generation of flat surface, how this flat surface can be generated. For say we take a point on a plane, all right, and then it is moved along a straight path. Along a straight path up to this much, and this is say an arrow. So, let us take a point. Yes, sorry. Now, you take a point and then let it move along a straight line, along a straight path, and then this straight line will be traversed in a perpendicular direction. Suppose it is moved in this direction. So, this straight line now proceeds, goes like this along this direction. So, the resultant of this movement of the straight line along this path will be the flat surface. This straight line or vector is called generatrix, and the other direction along which this straight line or generatrix travel is called directrix, simply D, directrix. This is one way of making flat surface. There can be another method. Suppose we draw it, we take a point and then draw a circle on the plane, and this is the generatrix, all right. And then you reduce the diameter of this circle gradually. That means the circle is gradually concentrating towards the center. That means it is moving in this direction. So this is the directrix. So combination of this generatrix, this circle, original circle, and the directrix together will constitute the circle or the surface. Now, see the generation of cylindrical surface. Now, cylindrical surface can be straight, taper, or formed. Let us say straight surface. You take a point, say here, a point. Now, you rotate this point about an axis. Just imagine an axis, and about this axis the point is rotated to form a circle, a circular path. This is showing elliptical because I am showing the 2D. So, this is the generatrix, a ring like circle. Now, this ring will be traversed in a direction parallel to this axis, along this axis. Okay. So, what will happen? This ring is traveling in this direction. So, this surface that will be produced by this ring while traveling in this direction, say this is called directrix, this will produce the cylindrical surface. Another method, we can take a straight line, simple straight line, say this is generatrix, and now this straight line will be rotated about a parallel axis. Now, this will be rotated about this axis like this, and this is the direction along which this straight line will be rotated. So, what will be the result? So, this straight line is now rotating about this axis, and this will produce this cylindrical surface. This will be straight because this straight line taken generatrix parallel to the axis. Now, taper. If we take this axis of rotation, this is the axis of rotation, and the generatrix in an inclined fashion, this is the generatrix. Now, if the generatrix is rotated about this axis, then this will be the rotation of this point, and this will rotate like this. So, what will be the result? When this straight line will rotate about this axis in the fashion shown, then this will produce this taper cylindrical surface, and this is the directrix along which this straight line generatrix is rotated. Now, formed. This is an axis, and you take a line like this, and you rotate this line around this axis, and then what will happen? This will form like this. So, this will produce a surface like this. That means, this is the generatrix, this is the generatrix which is rotated about this axis along this path, circular path. So, this is the directrix. Now, you produce this surface, a formed surface. Another example, you take a center line, and then a line like this, so this kind, and now you rotate. So, this is the generatrix, you rotate about this axis. So, this will be formed like this. So, this will produce this surface. So, this is generatrix and this is directrix. This is how various types of cylindrical surface, straight, taper, formed, can be produced. Now, come to tool work motions. In for machining work, the cutting tool and the workpiece will interact. There should be always a relative movement, and so both the tool and the work will be subject to motions, relative motions. Now, there are two kinds of motions essential for machining purpose. One is formative motions, one is cutting motion, simply CM, other one is feed motion. Now, I shall show you what. Say for example, in turning, suppose here is a rod, and this is the center line. Now, this is the tool, cutting tool. It is a turning operation. This side it is held in a chuck, and this side may be a tailstock. Now, what are the motions involved? So, this job will be rotated about its axis. So, this is cutting motion, and the cutting tool will be moved along this axis of the job. This is called feed motion. So, combination of this cutting motion and feed motion results this surface by removing the excess material, and this is the finished surface produced. This is the finished surface. Now, next is auxiliary motions, another set of motions which may not be compulsory, but it may be required sometime. For example, indexing motion, for example, in milling gear teeth. So, this is say a gear blank. You take a gear blank, a cylinder, all right, and now you cut a tooth gap like this with the help of a milling cutter. So, you produce this one. So, you can, yes, it is one. So, one tooth gap. After producing one tooth gap, then this will be shifted and this blank will be rotated by another tooth gap, and then this will produce another remove material from here. So, leaving a cutting a gear teeth in between. So, this way this will produce number of teeth by one indexing. This is called indexing motion. Then is say additional feed motion. If you consider the gear shaping process, cutting the gear teeth in gear shaping machine, this is the gear blank in which teeth have to be cut, and then this is the cutter, gear shaping cutter. Now, what are the motions involved? First of all, the cutting motion, the cutter will reciprocate, and then this is cutting motion, this will rotate, feed motion, then this will rotate in opposite direction, this is called indexing motion. In addition to these four motions, this workpiece has to be, blank has to be continuously fed or moved towards the cutter, so that the full depth of the gear teeth can be cut. So, this is called additional feed motion. Now, coming to relieving motion, for example, machining flanks of form milling. Just imagine this is the disc, we are manufacturing a milling cutter, a form milling cutter. So, what is the form of the tooth? This is one tooth, then this is another tooth, then this is another tooth, all right. Now, how to cut this profile on the disc? Originally this is the disc, now this has to be produced. So, you take one cutting tool like this, and this will be rotated in this direction, and the cutting tool will be moved in this direction. Resultant of this feed motion and this rotation will produce, this point will move along this path, this is the locus, and this one. After completing this path up to from here to here, this will come back again, then again it will cut this one. So, there will be reciprocating motion. This is called relieving motion, and the lathe in which this kind of work is done is called relieving lathe. Now, connections of generatrix and directrix with tool work motions, production of external cylindrical surface in lathe. Now, you see where the cutting motion, feed motion will be connected with the generatrix and directrix, and this is producing cylindrical surface. Now, say there is a blank, a rod, undergoing turning operation. All right. Now, what are the motions? This is feed motion, cutting motion, rotation of the job. This is cutting motion. Now, what we are producing? We are producing this surface, this cylindrical finished surface. This is the finished surface and is the finished cylinder. So, what is needed? Rotation of this job, that is related to the job, this point of the tool tip, this will, so this will create a rotation along this path. So, this is the generatrix, this is the generatrix, and because of feed motion, this point is also moving in this direction. So, this is the directrix. Now, here you observe that the generatrix is obtained from the cutting motion. So, generatrix is connected with the cutting motion, it is imparted to the job work, whereas the directrix is connected with the feed motion of the tool, feed motion, and imparted to the cutting tool. So, this is the indication how these generatrix and directrix are connected with the tool and work as well as cutting motion and feed motion. Now, the cylindrical surface can be produced in another way. Suppose there is a rod, here is a surface or a disc collar, and this is the rod. Now, you put the cutting tool in this fashion. The job will be, this will give the feed motion and the job will rotate, this is cutting motion. Now, here how do you get it? So, this is the generatrix, this is the generatrix which is a part of the cutting tool, and now this is travelling along this path, the circular path. So, this is the directrix and this is the generatrix from here to here. So, generatrix is connected with the tool and directrix is connected with the job, and this is connected with. So, generatrix is not connected with any motion, it is connected with the tool. So, there is no motion, but it is connected with the tool, say tool. And what about directrix? Directrix is connected with the cutting motion and the workpiece. This is how the cylindrical surface are produced. Now, production of flat surfaces in facing, by facing in a lathe. Now, people believe that lathe produces only cylindrical surface, but flat surface can also be produced in lathe. How? This is a rod, and this layer of material and this is the cutting tool. This cutting tool travels in this direction. So, this is feed motion, and then the job rotates, that is cutting motion. So, if you look, see from this side here, this is the workpiece, outer periphery. So, when this point is fixed, the job rotates, this is the locus of the contact point. So, this is generatrix. Now, the tool moves inside and removes this material gradually. So, this moves inside, that means the diameter of the circle is gradually reduced. and the metal is totally removed. So, this is the directrix. So, directrix is connected with the feed motion and the tool, and generatrix with the cutting motion with the job, and directrix with the feed motion imparted to the tool. This is how flat surface can be produced in lathe. Now, next in shaping machine, how flat surface are produced in shaping machine. Now, in shaping machine, this is the cutting tool, this is the workpiece, this is the flat surface which is being produced, and this is the excess material which has to be removed gradually. Now, what are the motions involved? The cutting tool reciprocates in this direction. So, tip of the tool moves along this path. So, that is the cutting motion, and the workpiece moves in this direction slowly. So, this is a feed motion. Now, come to this point. So, this surface, flat surface has to be produced. So, this cutting motion, which is a straight line, is equivalent to the generatrix. So, this is the generatrix, and this generatrix moves along this path, the directrix path, which is parallel to feed motion. So, this feed motion produces the directrix, and the cutting motion imparted to the tool produces the generatrix, and we get the flat surface. So, here the generatrix, this one is connected with cutting motion imparted to the tool, and directrix, it is obtained from feed motion imparted to the job work. Now, come to planing machine. Planing machine is very similar to shaping machine, only difference so far as generatrix and directrix is concerned. In shaping machine, the tool reciprocates, produces cutting motion, but in planing machine the tool remains almost fixed, the job reciprocates, and that gives the cutting motion. So, cutting motion is obtained by the travelling of the workpiece, and that produces generatrix. And directrix, the cutting tool travels slowly instead of the job. So, in case of planing machine, generatrix connected to the cutting motion obtained by reciprocation of the job workpiece, and directrix, this directrix will be accomplished by slow movement of the tool in this direction. So, this is feed motion and this is tool. This is how it is produced in shaping and planing machine. Now, to come to production of flat surfaces. Now, generatrix and directrix are obtained by. Now, here you see the generatrix and directrix are nothing but two lines. They can be straight line or they may not be straight line, they can be curved lines. But how are they obtained? Tracing. The examples I have shown in case of turning, shaping, there that generatrix and directrix are obtained just as a locus of a moving point, that is by tracing. So, that gives an example of tracing. Forming the form of the tool will give the generatrix. Then tangent tracing is another method, and generation. Now, I shall show you the different methods. Say example, tangent tracing, how that generatrix or directrix, especially directrix, will be obtained by tangent tracing in case of milling. Say suppose this is the milling cutter, a slab milling cutter, which has got number of teeth, a number of teeth, all right, and this removes material from the workpiece. This is the blank, all right. Now, this rotates in this direction. So, this is cutting motion and the job moves in this direction, that is feed motion. It moves in this direction, this is feed motion. And what does it do? It produces flat surface. This is the flat surface, finished surface, and this produces this flat surface. Now, this is slab milling cutter. which has certain length. So, this has got a length and the workpiece so this is the flat surface which is getting produced. How? So, when this cutter which is like a roller rests on a flat surface is a line contact. This line of contact is a generatrix. Now, here since it is a straight roller, this will be a straight line, but if it is a curved surface, a peculiar shape, then this will be also a non straight line curve. I am coming to that later on, but so this is generatrix, and because of the feed motion this point is moving in this direction. So, this is the directrix. So, result of this directrix and this generatrix. So, this straight line is moving gradually in this direction, resulting this flat surface. Now, what we can write? So, generatrix. Now, here again you just observe this cutting tooth removes the material along this path. Now, next cutting tooth will follow this path, the next cutting tooth will follow this path, it will go like this. So, this is the actual path, but the directrix is a straight line. That means, if you just imagine a straight line tangent to this curved path or the locus of the tip of the tool, then this is the directrix which is nothing but tangent to the instantaneous locus of the tip, and this is example of tangent tracing. This is called tangent tracing. Therefore, we obtain generatrix as it is not connected with any motion. So, no connection with the motion, it is connected with the tool. So, tool, the form of the tool, and we obtain by the form of the tool. It can be straight line, it can be curved like this, and then directrix, it is connected with the feed motion of the workpiece, and it is obtained by tangent tracing, TTR, which stands for tangent tracing. This is an example of tangent tracing. Next, you see generation process. In generation process, we get complicated surfaces by simpler form of the tool. That is the unique characteristics of generation. For example, we want to produce the teeth of gear, and then these are the tooth gap. Here is a cutter fitted on a plank. Now, if you rotate this plank or roll on the surface, this cutting protruded portion will gradually penetrate into this material and then gradually get out with the continuous rolling, and finally, this will leave an impression like this or cavity. So, this form of the cavity is not exactly same as the cutting tooth. Now, here how it can enter? This cutting tooth actually reciprocates perpendicular to the board here or parallel to the axis of the gear blank. So, this is a cutting motion, this reciprocates. It reciprocates like this, perpendicular to the plate, and then we get this one. It can be understood by another method. Suppose this is a disc or a gear blank on which the gear teeth have to be produced, and this is a plate or plank resting tangent to the surface, just like this, tangent to the surface. Now, this one is moving in this direction with a velocity v, and this one is rotating with an angular velocity omega and radius is r, such that is a rolling action. So, if for rolling v must be equal to omega r. At this point, there is no sliding movement. Now, if we have one protrusion like this, and now this is reciprocating perpendicular to the board or parallel to the axis of the gear blank, that is cutting motion. Now, it is gradually moving in this direction, this is also rotating. Now, this will gradually come close to this and then penetrate into this. When this will penetrate, this will remove this material, and finally, when this cutter with this protrusion or tooth, cutting tooth will reach here, by this time a tooth gap will be produced. So, this material will be removed. So, we get a tooth gap. Now, if we have another tooth side by side, say 2 teeth, then we will get 2 tooth gaps simultaneously, and in between 2 tooth gap we get 1 geared tooth. So, this is example of generation. With the help of very simple type of tool, you get a complex shape, say involute profile of the cutter. Now, here you see form milling. In this case of form milling, what we are actually producing, this is the milling cutter. This shows the milling cutter, and this is the workpiece, a cubical block in which a slot has to be cut, a groove, a V groove has to be cut. Now, we take the cutter with a V groove, V shape. So, for getting this particular shape of the groove, material removal, so this is this portion is the generatrix. And now, this generatrix, when it travels along this path, the directrix, we get this slot. Similarly, in this case, if we want a circular groove, so this is the generatrix, and this will travel along this direction, that is the directrix, we get this profile. Now, what are the motions involved? The cutter is rotating, cutting motion, job is moving in this direction, feed motion. The form of the tool gives the generatrix, and travelling of the feed motion of the job gives the directrix. So, in this similar here. So, we get this is the generatrix. In this case, the form of the tool is nothing but the generatrix. This is the generatrix. Now, in this case, generatrix is not connected with any motion. It is connected with the form of the tool, this form of the tool, all right. And but this form of the tool. But what about the directrix? Directrix is connected with the feed motion imparted to the workpiece, and this is obtained by tangent tracing, because it is a milling process, and a cutting motion is not connected with either generatrix or directrix. This is called form milling. Now, come to drilling operation. In drilling operation, what does drilling do? Drilling or drills produces or originates circular hole or cylindrical hole, straight cylindrical hole in solid body in a machine tool called drilling machine. So, it is a hole, hole means a cylindrical surface. Now, here suppose you want to make a hole, this is the upper surface and you are producing a hole in a solid body like this, and then this is the generatrix, a circular ring like. So, this is the generatrix, and this ring will be travelled along this direction, transverse to the plane or parallel to the axis, and then you get the hole inside. So, this is the generatrix and this is the directrix. The result of these two is the internal cylindrical hole. Now, in case practically it is like this. So, this is the drill bit. This is the drill bit and is the axis of rotation of the drill bit. Okay. Now, it is producing hole in a block. So, what are the motions? First motion is the cutting motion. The job rotates, the cutting tool rotates. Now, the cutting tool rotates, not the job, and the cutting tool moves downward, that is feed motion, and the job remains stationary, it does not move at all. The cutting motion is given to the tool and feed motion, result is, now this is the point of contact. Now, when this is subjected to rotation, now this point will trace a circle. So, this is a circle, this is a circle, this is the generatrix, and the feed motion that the cutting tool gradually moves downward. So, this is the feed motion and this is the directrix. What is the result? Result is the hole. We make this cylindrical internal surface. Now, what is boring? Vertical boring. Now, boring is similar to drilling, but difference is drilling originates hole in solid body, but boring enlarges and finishes existing cylindrical holes. So, it gives more finish and enlarges hole. Now, boring machine may be two types, vertical boring or horizontal boring. In vertical boring, the configuration, that is generatrix, this generatrix is connected with the cutting motion imparted to the tool. So, tool and obtained by tracing. Feed motion is also connected to the, directrix is connected to the feed motion of the tool, feed motion and tool. So, you see both are tool and obtained by tracing. But in horizontal boring, only difference will be the feed motion will be given to the workpiece. So, this will be W in case of horizontal boring. Now, machine tool drives. Machine tool requires drive. Machine tool drive refers to source and transmission of motion and power. So, electric motors that transmit power and motion both to the cutting tool and the workpiece. The sources of power and motion can be electrical motors, different types, or hydraulic power pack, hydraulic drive, and more common is electrical motors. Now, beside these sources of power, drive also include some devices. For machine tools need wide ranges of speed and feed, cutting velocity and feed. Why? For machining different jobs, say material, different materials are machined at different speeds. Strong materials, hard materials at low speed, low velocity, and softer materials at faster speed. If the job diameter is very large, so speed should be low, RPM should be low, and if the job diameter is low, then RPM should be large. Using different tool materials. Now, when you use very good tool material like carbide, we can machine at high speed, but if the tool material is high speed steel, then speed has to be maintained low. Now, various types of operations, turning operation, finishing operation are done at high speed, but operations like say reaming, thread cutting should be done at low speed. So, the machine tool should be able to provide all this range of speeds, varying degree of surface finish. If you want very good surface finish, the speed should be very high, and so on. Now, the machine tool drive may be two kinds, step drive and stepless drive. What is really step drive? Step drive means, suppose this is the input shaft which is rotating at a particular RPM. Now, this is the output shaft. From one input motion, we need large number of motions or speeds or RPM, say 1, 2, 3, 4, 5, 6, it can be say 12, 18, 24 like that. This is called step drive. That means, from one input speed we get few discrete definite number of and values of speed. This is called stepped drive. It is more economic. It is obtained by step pulley system, gearboxes, chain drive, and so on. But in another case, this is called stepless drive, where from inputs, simple one input speed, we need speed to the output shaft minimum or maximum or any speed in between, infinite number of speeds. This is called stepless drive. Say 500 RPM, 501 RPM, 399 RPM, any RPM from in between these two speeds, this is called range. Now, this can be obtained by cone pulley drive, PIV drive, positive infinitely variable speed drive, variable speed AC and DC motors, stepper motors and servo motors, hydraulic drive. Now, hydraulic drive has got certain advantages and disadvantages over electrical drive. Disadvantage, it occupies lot of space, leakage problem, and more floor space occupied. But there are advantages. First of all, it is smooth, it gives smooth operation, it is stepwise drive, and it gives self lubrication. Anyway, even then the motor drives are more common. Now, come to configuration and use of some basic machine tools. There are 100 types of machine tools or 1000 types, but now we are talking about basic machine tools. So, center lathe, again lathes are of maybe 24 type, we are talking about center lathe, which is most common, and this is the configuration of a center lathe. Now, what are the major components? Now, before we go into the component, let us see the workpiece. This is the workpiece, and this is the cutting tool which produces, which moves parallel to the axis feed motion, and the job rotates about its axis. So, job is subject rotation and tool axial motion. Now, this is called headstock. Function of the headstock to hold the job as well as transmit power and motion from this motor from here to this job. This is a tailstock. What is the function of the tailstock? It gives support to the job. It also sometimes holds some cutting tool like drill or reamer for doing that kind of work, reaming and drilling. And the cutting tool is mounted on the tool holder, which is on the tool post on the compound slide on the cross slide on the carriage. This carriage which travels along this bed. So, the first important part is headstock, then tailstock, then carriage. This travels over the bed. So, this is the bed, and the bed is standing on two columns, and the two columns rest on what is called foundation. What are the operations? Common operations? Common operations are, say, turning. Now, the turning can be, the turning can be external or it can be internal. Now, this is external turning, job is subject to rotation and the tool is given the feed motion. Internal turning, it is similar to boring like this. Now, facing, this surface is getting produced, flat surface. So, the job rotates and the tool moves. This is internal facing, this surface is getting faced. Then grooving, we produce a groove, this is a cylindrical surface. By moving the tool inside radially like this feed motion and job rotates cutting motion, we get this groove, and this is internal groove produced in a cylindrical surface. Now, we want a particular form of the job, particular form like this. This is called forming. For that, the cutting tool should possess the same form or the profile, replica of the form of the job. So, this is external forming and this is internal forming. So, we want an internal form like this, and this is the cutting tool which has also got similar form. Now, when the job rotates and this is moved in this direction called feed motion, we get this particular profile. And thread cutting, threading. So, this is a number threads are cut by what the movements, rotation of the job and faster feed of the tool, and this is internal thread cutting. Now, come to shaping machine. Shaping machine produces flat surface. It can, flat surface may be horizontal, vertical or inclined. This is the cutting tool, the cutting tool tip. The cutting tool is mounted on the clapper box which is fitted into the ram. The ram reciprocates with a large stroke length on the housing or the bed or structure. So, this travelling of the tool reciprocation gives the required cutting motion. What about the workpiece? This workpiece is mounted on a vice. Vice is fitted onto the table, and the table moves along with the job in a perpendicular, in a direction perpendicular to the cutting motion in this direction. So, here along this axis perpendicular to the plane of this diagram, all right, and then we get flat surface. So, this is the flat surface here, and this produces flat surface. Now, the planing machine, as I told you earlier, the planing machine and shaping machine are basically same. In shaping machine, the tool reciprocates. In planing machine, the job, this is the workpiece which is mounted on the table, that reciprocates onto the bed. This is the bed. Whereas, in planing, in shaping machine, the feed motion, the transverse feed motion was given to the job. It was moving perpendicular to the plane, all right, horizontally slowly. But in shaping, in planing machine, the feed motion, the slow feed motion is given to the tool. So, this will move in this direction perpendicular to the cutting motion. So, what is the difference of planing machine from shaping machine? First difference is that in generics and directrix, or the cutting motion is given to the job in planing machine onto the tool on shaping machine. Feed motion is given to the tool in planing machine and job in shaping machine. Another big difference is the shaping machine is used for small jobs, low duty small jobs, but planing machine is used for heavy duty jobs, heavy jobs. Now, come to drilling machine. What is the configuration? This is the drill bit which rotates about its own axis and it moves downward gradually, that is called feed motion. So, both the feed motion and cutting motion is given to the drill bit. Job remains stationary onto the bed, resting on the base, and this is called the structure or body of the drilling machine, and this is the spindle which moves up and down. It rotates as well as it moves up and down, and this is the power source, and this is the gearbox which changes the rate of speed or the RPM of the spindle as well as the rate of travel of the spindle, called feed motion. This produce what are the applications? Applications generally to produce cylindrical, straight cylindrical hole of different diameter. This can be also used for counter boring, counter sinking, and some similar operations like tapping with a special tapping attachment, like that. Now, come to milling machine. In milling machine, this is the cutter and this is the workpiece. So, this rotates about this or on this arbor. The arbor is receiving motion from this source and there is a gearbox inside, and this is the ram which can be time to time adjust, position can be adjusted. The workpiece is mounted on the table and table is fitted onto the bed. The bed has got three movements. The workpiece along with the table and bed can move axially perpendicular to this plane, to this plane of the plate, and the transverse motion in this direction and vertical movement upward and downward, resulting various surfaces. And this is the speed gearbox which splits the speed into number as desired. This is a feed gearbox. Now, what are the functions it does? It does various kinds of operations, common applications of milling machines. Now, common, there can be some uncommon applications also. For example, surfacing. This is the milling cutter, this is the workpiece producing flat surface. Here slotting, this cutter produces a slot, a straight slot. Slitting, a plate is cut into two pieces by a slitting cutter. Now, here we make a groove, a V groove, called operations called grooving by a grooving cutter, and now you produce a form contour, all right, and that is called forming, and the cutting tool has also got a similar configuration here, which will be the replica of the profile of the job to be developed. So, this is milling. Now, come to machine tool specification. How to specify machine tools? When you go to market for purchasing say a lathe, you have to tell what kind of lathe you want, what amount of power, what kind of lathe, then what should be the size of the lathe, and what can, and all these things you should be very clear, you should very clearly mention, otherwise you cannot purchase it, procure it. Now, how lathes are specified? For example, central lathes, maximum diameter and length of the job that can be accommodated. Earlier days, the lathe was specified by length of the bed. Length of the bed is not that important, but what is more important, maximum length of the job and maximum diameter of the job that can be accommodated is the most important part that you have to mention. Power of the main drive, that is called kilowatt. Then range of spindle speeds, what is the minimum RPM, what is the maximum RPM, what are the intermediate speeds, Then range of feeds, rate of travel, the millimeter per revolution, different feeds are there, slow feed, high feed, medium feed. So, range of feed has to be specified. Then space occupied by the machine. Earlier the volume of the machine or weight of the machine was considered as the specification, but now it has been realized that no, the space occupied, which is very important and expensive, should be considered. Now, say for shaping machine, in shaping machine the length and breadth of the bed, that will decide the length and breadth of the job will be first specified. Then maximum axial travel and vertical travel of the bed, the length of travel in two directions, maximum stroke length of the cutting tool, range of number of strokes per minute. So, the number of strokes per minute can be slow or can be fast, range of table feed, the feed motion is given to the table. So, that can be fast, slow, and this range should be mentioned. Power of the main drive, say 11 kilowatt or 5.5 kilowatt, like that, and similarly space occupied by the machine. Come to drilling machine, maximum drill size, maximum diameter of the drill, which will decide the maximum diameter of the hole that can be produced. Size and taper of the hole in the spindle, say Morse taper, range of spindle speeds, say what is the minimum RPM, what is the maximum RPM, number of speeds, and what are the steps. Then range of feeds of the tool travel, power of the main drive, range of the axial travel of the spindle, and floor space occupied. Now, milling machine type, ordinary type or swiveling bed type. The bed can be rotated slightly in addition to x, y, z movement. Size of the workpiece, work table, range of travels of the table along x direction, y direction, z directions. Arbor size, the diameter, the bore diameter of the cutter will be decided by the arbor size. Power of the main drive, say kilowatt, range of spindle speeds or the arbor speeds, range of table feeds in x, y, z directions, and floor space occupied. Now, classification of machine tools. How many machine tools exist? How many types of machine tools? When we were student like you, we asked our teachers how many types of machine tools really exist. Our teacher told more than 10,000 types of machine tools exist, but gradually the number is decreasing with the concept of group technology. With the help of group technology, the total number of machine tools or the variations is gradually reduced for convenience. Now, let us talk about the broad classification of machine tools. Now, with respect to what the classification has to be made according to configuration. So, when you say classify the students, say classify according to what? According to height or weight or qualification or other caliber, like that. Similarly, when you talk about classification of machine tool, that is according to what? According to configuration, direction of main axis, horizontal, that is horizontal lathe. There can be vertical lathe also. Milling machines are maybe vertical axis, horizontal axis, inclined. This is very special for transfer machine. Then according to purpose, general purpose, any kind of work on any type of job. Singles purpose, which is more productive, that is only one operation, say only turning or only facing will be done on different types of jobs. Special purpose, a definite number of operations will be done only one type of job repeatedly for mass production. Next comes according to size duty, heavy duty, say boring mill, planing machine, like that. Medium duty, say milling machines, lathes, small tabletop drilling machine, micro size, micro drilling, and so on. Then according to type of blank, blank may be bar type, chucking type, and housing type. Housing type are generally big machine tools. According to precision, ordinary or precision, even high precision. This way machine tools can be classified. According to the degree of automation, so machine tools need automation. It can be non-automatic like central lathe, semi-automatic like capstan lathe, turret lathe, automatic like single spindle automatic lathe. Then according to type of automation, it can be fixed or hard automation. Most of the common machine tools that you see, those are fixed or hard automation, that which produces only one particular type of job. If you change the job, then lot of changes have to be incorporated into the machine tool. It is very expensive and this will take a lot of time. Flexible automation, this is the modern concept where the changeover of the job can be very quickly accommodated by using the computer or numerical control machine tool. according to number of spindles. Now, most of the machines say lathe, it has got single spindle, only one spindle is there, but it can be multi spindle also, say 2 spindles or 4 or 6 or 8, they call multi spindle lathe, which gives more productivity. And finally, lastly, according to system configuration, standalone type, most of the machine tools I talked about are standalone, only one machine in one place, or machining system, say 3 or 4 machine tools will be amalgamated into one to carry out various types of work like drilling, milling, boring and so on. These are called machining system, example machining center. Now, some exercise for your practice. Show the tool work motions and the generatrix and directrix in external thread cutting in center lathe. Also state how those generatrix and directrix are obtained. This is question number 1. Second question, which conventional machine tools flat surfaces can be produced? Third, state the major differences between shaping machine and planing machine. I already told. In which machine tools both the cutting motion and feed motions are imparted to the tool? How is feed expressed in turning, shaping, drilling and milling? See the answers. Now, answer question number 1. This is thread cutting. So, job is rotated cutting motion, this is the feed motion. Now, this is the generatrix and this is the directrix, all right. So, this combination of directrix and generatrix produce this surface, these helical grooves. This helical groove, generatrix is connected with the form of the tool, no motion, but it is a part of the tool and the form of the tool. So, F. What about the directrix? It is the resultant motion of the cutting motion and feed motion. So, this cutting motion and feed motion jointly produce the slant motion. Then is a combination of tool and job both, and this is a tracing. Now, question number 2, flat surfaces can be produced in center lathes, for example, by fleshing, shaping, slotting and planing machines, milling machines and so on. Now, this is the difference between question number 3, difference between shaping and planing machine we already discussed, and you can see the size of the job is small and big. This is a planing machine, is a mistake, this will be planing machine. Tool reciprocates, the job reciprocates. Feed motion is given to the job, feed motion is given to the tool. And this is the generatrix and directrix. Generatrix is given obtained by cutting motion of the tool and by tracing, directrix by feed motion of the workpiece. And in case of planing machine, the cutting motion is given to the workpiece, feed motion to the tool. Question number 4. Both cutting motion and feed motion is imparted to the tool in drilling machine, vertical boring machine. These are the characteristics of these 2 machine tools only. Answer to question number 5. How feed is expressed in different machine tools? Turning, millimeter per revolution, shaping, millimeter per stroke, drilling machine, millimeter per revolution, milling machine, millimeter per minute or centimeter per minute. So, this is how, and in different machine tools it can be defined, like in broaching machine by tooth rise and so on. Thank you.